Okay, so now we're going to go over an example of an application that involves an accelerating control volume. So here we have a water, it could be from, say, your garden hose, is shooting out a spray of water of cross-sectional area, a jet. This jet then strikes a cart that has a vane on it. The vane turns the jet upwards at some angle theta. And due to the change of momentum of the jet, this cart will accelerate to the right. And what the problem is asking us to find is the velocity of the cart as a function of time and the reaction force on the wheels of the cart as a function of time as well. Okay, and so we are to find the velocity of the cart as a function of time, and the reaction force as a function of time in the y direction. Okay, and we know the mass of the cart, we know the angle theta, we know the velocity of the jet, we know the density of the liquid, and we know the area of the jet. And we are to assume that the area of the jet does not change as the jet moves and is turned by the vane. It's a pretty, not the best assumption in the world, but it works well enough for this problem. Okay, and so we're to find these. And so I guess where do we begin? So first, let's just start with the assumptions like we always do. Okay, so one, we'll just write the assumption that we just stated, but we'll assume constant area of the water. Okay, so constant area of the H2O. Two, we will assume the CV moves with the cart. So our strategy is we are looking to find the velocity of the cart. And so it is natural, for that we do not pick a stationary control volume. So if we picked a stationary control volume that looks something like this, and the control volume did not move, eventually the cart would move outside of the control volume and we wouldn't be conserving anything of interest. So instead, we need to choose a control volume that surrounds the cart and then moves with that cart. Okay, and so, and this control volume, it's non-deforming, so we're just assuming it's going to move with the cart. So basically all points of the control volume move with the cart. And because of that, we can use the equation that we derived earlier for conservation of momentum. Okay, we'll assume constant density. Rho of the water should be specific. 4, we'll assume uniform flow. Okay, what I mean by that is that at any position along the jet, the velocity at the top will be the same as it is in the middle, will be the same as it is on the bottom. And at this station here, the velocity, the mean velocity might be different, but it'll be the same on the top as it is on the bottom of the jet at any location. Okay, 5, we will assume a constant mass of H2O in the vane. And the vane is the portion of the cart that is turning the flow. Okay, in a way, this is a consequence of assumption 1. This basically means that the vane is always full with water. So basically, this section here always has water. The entirety of the section of the control volume that contains water always has water in it. So we are neglecting the portion of the flow where, say, if you just turn the garden hose on, and for a brief instant, you'll have a scenario where the jet of water is still moving across the jet, and basically half the cart is covered by water, and the other half is still covered by the air. We are neglecting that portion of this. So basically, this picture here holds at all times. Okay, 6. we will assume that the mass of the cart is much, much larger than the mass of the water in the control volume. Okay, so basically, we're assuming that this jet area is actually fairly small, so that the mass of the water in this section here is much smaller than the mass of the cart in this section here. Okay? And we are going to neglect accumulation of H2O momentum in the control volume. And these assumptions here, I developed those using experience, and I didn't know to do these beforehand until I started solving the problem. And so, in general, you wouldn't know to do this one until you came across a term that you didn't know how to deal with, and then basically, so normally you feel free to leave room for additional assumptions that you need to make as you go. Okay, so solution. So we've listed our assumptions, and as I said before, our strategy is to use a control volume that moves with the cart. Okay, so our control volume, I'm gonna copy this. We're gonna select the control volume to basically follow the cart. Okay, so our control volume will look kind of like this. And the velocity of the control volume will equal the velocity of the cart. Okay, and we'll do a little XY coordinate system here. And I'll just say that the velocity of the cart, since it's restricted to go only in the I hat direction, we're assuming it's not going to lift off or anything like that. So that would equal just V cart I hat. Okay, and we're assuming that the control volume basically moves along with this cart. And so our strategy will be to apply conservation of mass and conservation of momentum on this control volume here. And note, in theory, you could choose, you could just choose a control volume that encompassed the water, but the issue with that would be that you wouldn't know what to do with the forces on this bottom part here. So just like in thermodynamics, you can choose a control volume where there is an edge that you don't know what to do with. And so if possible, you can deal with that unknown by just making your control volume to surround and enclose that that unknown portion with a larger control volume that that completely encloses that, but it goes around sections that you know what to do with. Okay, and basically we know what to do with all of these surfaces here. Okay, and so we just really need to go through and apply the conservation laws. Okay, and one thing I will note that here we have been using that V, or the relative velocity between the control volume and the fluid, which is equal to V of the fluid minus the velocity of the control volume. In this case, we cannot make the usual simplification that this is 0, and the relative velocity is just the velocity of the fluid. In this case, that does not work. So what we have to do is use this, basically use this as is, and just keep very close tabs on what everything is. And using the fact that the velocity of the control volume is just the velocity of the cart, this equals the velocity of the fluid minus V cart I hat. Okay, so now let's write down our conservation laws. And we have a conservation of mass. Okay, and as I said before in a previous video, I just get used to writing that one down first because we almost always need it. So we just write conservation of mass, so that's partial t, acting on the integral of rho dv over the control volume, plus the surface integral of rho times the relative velocity dotted with n hat dA over the entire control surface, and that's equal to 0. So now we'll start applying our assumptions and simplify this as much as we can. Okay, well, the integral of rho dv is just the mass in the control volume. And if we look at our control volume here, we have the mass of the cart plus the mass of the water, okay? And again, that's the total mass in the control volume. So this equals the mass of the cart plus the mass of the water, okay? And we can assume that this is small, okay, compared to the mass of the cart. So this is approximately the mass of the cart, okay? So then this implies that partial t of mcv equals partial t of m cart plus m H2O, which again I argued that basically this is small. This equals partial t of the cart mass, and this is also equal to 0 because the cart mass is constant. Okay, and I guess that's something that we should probably add in one of the assumptions. It's a pretty obvious one, 8, a constant cart mass. So feel free to add additional assumptions as you move forward, okay? And also, we don't need to invoke our small H2O mass here because we assume that the mass of the water in the vein is also constant. And so the time derivative of the H2O mass, even if we were to include it, is still 0. So basically what this means is that this time rate change of mass in the control volume is exactly 0, and conservation of mass becomes the integral over the control surface of rho vxyz dot n hat dA, and that's equal to 0. Okay, and so this is what conservation of mass turns into. Oops, sorry about that. Okay, and now before I start drawing a control volume, I will work with conservation of momentum just to see what terms we need to include before I start drawing the control volume and free body diagram. Because then if I need this integral for conservation of momentum, just multiplied by vxyz, then I will basically form both of these integrals together, because a lot of them, because they need the same information. Okay, so conservation of momentum. Okay, and we're going to apply the variant for a non-deforming, accelerating CV, and that's the one that, again, I ask you guys to start with on all your homework problems and things like that, and then cross out the terms you don't need, and you usually don't need all of the terms. Okay, and that one reads the time rate change of the control volume velocity. Again, we're assuming it's non-deforming, which means that the control volume velocity is spatially uniform, and that means it can only be a function of time at most. Okay, and this is multiplied by the integral over the control volume of rho dV plus partial t of the volume integral of rho times v xyz dV plus the integral over the control surface of v xyz rho v xyz dot n hat dA is equal to the sum of forces acting on that control volume. So now we can start simplifying things. So first, we will work with this term over here. This here is again just the mass of the control volume, or the mass within the control volume, and that equals the mass of the cart plus the mass of the H2O, and we are neglecting this, so small. And it's not that its magnitude is small, it's just that it's very small in comparison to the mass of the cart. Okay, so this term here simplifies to the mass of the cart. Okay, which is nice. This is just mass times acceleration. So now we will work with this term here. So I'll work with that down there. And what that term becomes is I can expand this to include we can integrate over the portion of the cart and the portion over the water separately. And so really what we can do here is integrate is basically break this integral up into its pieces. So partial t times the integral over the control volume CV of rho v dv xyz dv, and this turns into we can basically break this into separate volume integrals over the water and the cart. So this is partial t of the integral over the volume of the H2O times rho H2O v xyz H2O dV plus the volume integral over the cart itself, so that's the volume of the cart, times the cart density times v xyz of the cart dV. Okay, so basically all I've done was I took this volume integral here and I broke it into a piece over the cart and a piece over the water. Okay, so I can work with this term here, and this looks like I made a big mess of it, but both of these terms are zero. So what, and the reason that the reason why this is zero is v xyz, that the relative velocity of the cart equals the velocity of the cart, that's how fast it's going, minus the velocity of the control volume. Okay, and the control volume is just the velocity of the cart. Okay, and so really the relative velocity is just the velocity of the material minus the velocity of the cart. And since we are integrating over the cart volume, the velocity of the material is just the velocity of the cart. So this equals the zero vector, which means that this is equal to zero, and that's not an approximation, that is exact. And this term here with the water, where you have the v x y z for the water times rho H2O, this one we are going to neglect, and that is a true assumption. Okay, and essentially what we are assuming is that this is small compared to the mass of the control volume times d v cart dt. Okay, and so we are assuming that basically this is small, and we can get away with that because we are assuming that this mass of water here is very small compared to the mass of the cart. So we're not introducing too much error by neglecting that. Okay, and so that means that this term here goes to 0. And then conservation of momentum simplifies to the mass of the cart times dv cv dt plus the integral over the control surface of v xyz rho v xyz dot n hat dA is equal to the sum of the forces. Okay, and the velocity of the control volume is the velocity of the cart, and that equals v cart I hat. Okay, where v cart is just the velocity magnitude of the cart, and the I hat means it's just going in the positive x direction. So then conservation of mass conservation of momentum, turns into, we have the mass of the cart times its acceleration, dt, and that's in the I hat direction. Do not forget that conservation of momentum is a vector equation, so just make sure that if there's a unit vector that you maintain that, just to keep everything straight. And these problems look really complicated, but after you do a few of them, they're actually not too bad. It's just really a lot of bookkeeping. But if you do it with discipline and you do it rigorously, you will eventually get the hang of it, and it won't be too bad. So then we got plus the integral over the surface of v xyz rho v xyz dot n hat dA, and that's equal to the sum of the forces. Okay, so now we can't do anything with this term here because we have a moving control volume. We cannot turn the vxyz's into the fluid velocities. Okay, because the velocity of the control volume is not 0. So we do need to leave that term as is. Okay, so we have our expressions of conservation of mass and momentum that we need to evaluate, and the terms that we need the surface integral of rho v xyz dot n hat dA, the surface integral of v xyz rho v xyz dot n hat dA, and the sum of the forces to proceed. Okay, and so then to find these, I will do both of these together in the same step, and by basically finding finding the surface integral of eta rho v xyz dot n hat dA over the control surface, where for conservation of mass, eta equals 1, and for conservation of momentum, eta equals v xyz. Okay, and I'll do them together just to avoid writing a whole bunch of control volumes and doing and repeating a bunch of work. Okay, but we also need the sum of the forces. So really, I will write the control volume and the free body diagram. Okay, again, I will examine the control volume and the free body diagram. So for momentum, we have dp, dt. I like to draw the acceleration and the control volume on the left, and I like to draw the free body diagram on the right. Okay, and so here we'll do the control volume over the vane. So we'll draw the vane. Okay, and we have the jet of water right here. Okay, and it's at some angle theta. And I will draw the control volume to cut across the water normal to the outflow area. It'll follow just on the outermost streamline of the water jet. Then it'll go straight down, and then it'll follow around and follow the cart. Okay, and so I will call this the inlet area 1. The outlet will be area 2. The sides here around the cart, I'll call this area 3, where there's really no material flowing in or out. And I will call this area here area 4, and I'll say that the CV, or the CS here, CS4 follows outermost a streamline. Okay, and you don't have to do it that way. You could also choose it to the control volume to look like this, and that would also be a perfectly acceptable way to solve this problem. Okay, but I will call this curve section here section 4. Okay, and so we draw our n hats. We got x, y, and we draw our x hats. We know that the control volume is moving at some v cv, which is just the cart velocity. We know that n hat 1 points to the left, and I'll get rid of these. And we know that there's some fluid velocity v1 here. And I will write those more carefully later on. N hat 2 points up away in normal from surface 2. And we know that if you are riding along with the cart, to you it will look like that the water jet, if I were to shade that in, would just follow the surface of the vane here. Okay, and so essentially what this means is that this velocity here, we don't know what the fluid velocity is, but we know that to you, the observer moving with the cart, it looks like that the jet of water is being turned by this angle theta. So basically what we can say is that this velocity here is v x, y, z at 2. That is really all we can say, and that is equal to some velocity magnitude v x, y, z 2, and it is in the direction of n hat 2. And so that's really all we can say about that velocity vector at this time. Okay, and so now we'll do the free body diagram, because we have the sections that have velocity in them. Okay, and then draw the cart. Okay, the free body diagram is fairly simple. We have the reaction force in the y. We have the weight of the cart, so that's m cart times g. And we have the weight of the fluid, which we are going to neglect. Okay, and that was in the assumptions. Okay, and so we are neglecting the weight of the fluid. So our forces are quite simple here. We only have the weight of the cart and the reaction force holding the cart up. That's it. Okay. So now we will start working with the two integrals that we need and the sum of the forces. I'll do the sum of the forces first. Those are pretty straightforward. So the sum of the forces equals Ry in the j hat direction minus the mass of the cart times g, and that is in the j hat direction. Okay, and so this is what our sum of the forces are. Now we need to form the integral, and like I said, I'm going to do it in a generic fashion so I can sort of do both of them at once. So then the surface integral of eta rho times the relative velocity dotted with n hat dA, that equals, and again, this is a surface integral over the control surface, so we need to walk around the entire control surface and completely enclose the loop. And we have four different areas. We have basically area 1 here where the water is flowing in. We have area 2 where the water is flowing out. We have area 3, which is along the edge of the cart. And we have basically area 4, which is following the outermost streamline of the water jet. Okay, so it's encompassing all of the water. It's just following the very outer edge of the water. Okay, and so this equals the integral over area 1 of eta rho v xyz dot n hat dA1. We can't do anything with that term yet. We actually need to evaluate it. Then we got the integral over A2 of the same thing, eta rho v xyz dot n hat dA2 plus the integral over area 3, which is along the cart, of eta rho v xyz dot n hat dA plus the integral over area 4, which is the very top, along the water, eta rho v xyz dot n hat dA. Okay, so we can actually cross this term out here, and that's the edge of the cart. There's simply really no mass along the edge of the cart, okay, because it's just outside of it and we don't care about it, so there's no mass crossing that. You could also argue, if you were to put the edge of the control volume right on the cart itself, you could also argue that the same term would also be 0. And the reason for it being 0 is that Vxyz, that is equal to Vxyz equals V of the velocity of the material minus the velocity of the control volume. And this piece here is along the edge of the cart right here. Okay, and so the velocity of that edge is just the velocity of the cart, and the velocity of the control volume is also the velocity of the cart, and this equals 0. So basically this term goes away. So you can either cross this term out, basically either assuming that there's no mass crossing through this control surface because it's either outside of the cart or it is along the very edge of the cart, and that cart material and control volume are moving synchronously, so there's no net flow of material through this bottom here. Okay, now we got area 4, and area 4 is this piece along the upper edge, and we're choosing that to follow a streamline. So that follows a streamline. So this follows, not flows, follows the streamline. And in a moving frame of reference, recall that for a stationary frame of reference at V dot n hat equals 0, that's stationary. And for the moving reference frame, V xyz dot n hat is equal to 0 moving. So essentially then, along that upper streamline, Vxyz dot n hat is equal to 0 because, again, no mass crosses the streamline. So That's also 0. It's just that the streamline is in the moving frame of reference. Okay, so now we have to evaluate. Evaluate these two terms now, and you could also, this sort of last term here. You could also do the control volume just outside of the water, and then there wouldn't be any material flowing through that because you really don't care about the air relative to the water. There's, that would be such a small portion of it that you can neglect it to. Okay, so there are multiple ways that you can justify not including the contribution through the suture, and either way you do it, there's simply no material crossing through that portion of the surface. Okay, and there is one force I did forget about. Okay, and that is on all of these surfaces we have PATM. Okay, but the integral, but the net pressure force is the integral over the surface of P and hat dA, and that would equal minus the surface integral of P ATM and hat dA, and that's equal to 0 because PATM is constant. Okay, and so that's why in the sum of the forces I did not include the pressure forces, because this here is a free jet that's being turned, and the pressure just as the jet exits and just before the jet enters has to be like atmospheric pressure, and there's atmospheric pressure pushing from the top and the sides and from the bottom. Okay, and so basically the pressure is perfectly constant over the entire control surface, and if you integrate a constant surface over a enclosed surface, that integral is equal to 0. I've proven that multiple times. Okay, so now back to forming our integrals here. We need to form the integral over this this A1 here, where the water is entering the control volume, and A2 here, where the water is exiting the moving control volume. Okay. So now we will work with those in turn. Okay, and when things start getting complicated and you're involving multiple pieces, I always like to draw a portion of the control volume just to help me keep things straight. Okay, and so we have our control surface here. So we'd have n hat 1 equals minus I hat. We have the fluid velocity going in, that is Vj I hat, that is the fluid velocity. And also we have that VCV equals V cart I hat. Okay, and so now that we know all of these pieces of information, we can go through and basically form our two integrals that we need. So we have n hat 1 equals minus I hat, V1 equals Vj I hat, and VCV equals V cart I hat. Okay, and that equals the velocity of the control surface on station 1. Okay, so V XYZ at station 1 is equal to V1 minus the velocity at the control surface of 1, and because it's a non-deforming control volume, the velocity of the control surface is equal to the velocity of the control volume, and this is in turn equal to the velocity of the jet I hat minus the velocity of the cart I hat, and this implies that V XYZ 1 equals the velocity of the jet minus the velocity of the cart I hat. Okay, and we can't do anything more with that. Okay, and then the integral over area 1 of eta rho and eta rho V XYZ dot n hat dA1 is equal to, we can assume, we can do this dot product here, and I'm not going to show the details of that because this is just Vj minus Vcart I hat dotted with minus I hat, and so it just becomes minus Vj, the negative of the quantity Vj minus Vcart. Okay, and so this equals the integral over A1 of eta rho times negative Vj minus Vcart dA1, and we'll assume, we are assuming uniform flow at basically every station along the path where the flow is turned, so we can pull this out. And so this equals minus eta rho Vj minus Vcart, the integral over A1 dA1, with this is in turn just A1, and that's equal to the jet area. Okay, that's by definition the jet area. And so our integral here is then equal to minus eta rho of Vj minus Vcart times A jet. Okay, now we can evaluate this for both continuity and momentum by just changing eta. So for continuity, that's conservation of mass. Eta is equal to 1. So this implies that the integral over A1 of rho Vxyz dot n hat dA1 is equal to this expression here with eta set to 1. So this equals minus rho Vj minus Vcart times the jet area. Okay, and so we have the integral for conservation of mass, and for momentum, Vxyz is equal to eta. Okay, and Vxyz is equal to V1 minus Vcart I hat. Do not forget that the velocity is a vector, so we need the I hat or some sort of unit vector multiplying the magnitude. Okay, because it needs a magnitude and a direction. Okay, so then we apply the same formula but with eta equal to this, and we have the integral over A1 of V xyz rho Vxyz dot n hat dA is equal to minus rho, and I'll just cut to the final answer, V1 minus Vcart squared A jet I hat. And in your homework, I would prefer that you show a few intermediate steps just to show me that you know what you're that you know what you're doing. Okay, so for both surfaces, integrals, we have formed one piece of it. So now we got to form the second piece, and that is over the exit area. So area 2. Okay, and then again, I like to draw a little zoom in of that portion of the control surface to keep everything straight. And so we have n hat 2, and that's at some angle theta. And n hat 2, it was equal to cosine theta I hat plus sine theta j hat. So now we actually need to keep track of which direction it's in because that matters for the force. And the only thing that we can, and we don't know what, and we don't know V1, or we don't know V2. And so I'm just going to write the relative velocity as v xyz at 2 is equal to the magnitude of the relative velocity at station 2 times n hat 2. Because again, I argued that we know that if you're riding the cart to you, it's looking like that the vane is turning the flow by angle theta. So you know that n hat 2, and you know that the water is leaving it. So you know that the velocity of the fluid leaving here, oops, wrong one, is it must also be in the direction of n hat 2. Okay. And we will, and actually we have to use conservation of mass to find what that is. Okay. Then this implies that v xyz at 2 dot n hat 2, well, that's n hat 2 dotted with n hat 2, and a unit vector dotted with the same unit vector is 0. I mean, 0 is 1, sorry, 1. So that equals v xyz at 2. And you could also substitute in the cosine theta and sine theta thing. And if you do that, you will basically wind up with a cosine squared theta plus a sine squared theta, which is 1 times this. So you wind up with the same result. You can do it either way. Okay? So now we know all the pieces that we need to form the integral. So now let's work with that. So the integral over a2 of eta rho v xyz at station 2 dot n hat 2 dA2, that is equal to, well, first I'm going to assume that everything here is uniform. So you can pull that out. And so this equals, and then this dot product here is just v xyz at station 2. And so this equals eta rho v xyz at 2, and then we would have then what's left of the integral would be just the integral over a2 of dA2, and that's just a2 as normal. Okay, and a2, because we are assuming that the jet area is constant, that is a jet, and we can assume that because that's constant jet area, which we would which we have assumed. Okay, so now we know that integral. So now we just do the same thing that we did before and apply it to conservation of mass, and that's eta equals to 1. So then the integral of a1, or a2 I should say, of rho v xyz dot n hat dA2, that is equal to this expression here with eta set to be 1. So that equals rho v xyz at 2 times the jet area, which is a2. Okay. And for conservation of momentum, eta equals v xyz at 2, and that equals the velocity magnitude xyz at 2 times the unit vector, which is cosine theta I hat plus sine theta j hat. Okay, and so then the integral over a2 of v xyz of rho v xyz dot n hat dA2 I should say, is equal to rho v xyz2, that's squared, because we have one v xyz from basically here, and another one from the dot product, times the jet area, times its direction, or the unit vector, which is cosine theta I hat plus sine theta j hat. Okay, so now we know all of the pieces of the integral. So now we can start to basically put them together and find the total surface surface integral of rho v xyz dot n hat dA, and that will be equal to the integral of a1 of rho v xyz dot n hat, and that equals minus rho times vj minus v cart times a jet plus rho times v xyz, or its magnitude at station 2, times the jet area. And the same thing for conservation of momentum, the integral of the control surface of v xyz rho v xyz dot n hat dA, that is equal to minus rho vj minus v cart squared a jet I hat plus rho times the velocity magnitude, or the relative the magnitude of the relative velocity at station 2 v xyz 2 squared, times a jet times the unit vector, which is cosine theta I hat plus sine theta j hat. Okay, and so that is what these turn into, and we can work with this a little bit, and this will equal to I'll leave this alone for the time being. Okay, so now we know the sum of the forces, and we know both of the surface integrals. So now we are ready to go to the conservation laws. So back to conservation laws. Okay, and so mass turned into the integral over the control surface of rho v xyz dot n hat dA is equal to 0, and we have that integral directly above. So this implies that, and I'm just going to copy it in the interest of time, and this implies that this is equal to 0. Well, this here is a jet basically multiplies both terms, and the density multiplies both terms. And I should be explicit. This here is for the water portion, so this would be rho of the water and rho of the water. Okay, and then you can see that we don't know what this term, we don't know what the velocity magnitude at station 2 was, but we can now solve for it. And so this implies that v xyz at station 2 equals the velocity of the jet minus the velocity of the cart. Okay, and that's the same as the velocity magnitude at station 1, which this makes sense that since the jet area is the same on both and the density is the same on both surfaces, that means to conserve mass that the relative velocity it had to be invariant as that jet moves across the vane. It just changes its direction. Okay, and so conservation of mass told us something very useful, It gave us a piece of information that was not obvious, at least to me. And so now we work with momentum. And momentum, that was the mass of the cart times the acceleration of the cart in the I-hat. And recall that momentum is a vector equation. So to keep everything straight, you are going to have to write the I-hats and the J-hats all the time. Okay, and that is added to the surface integral of the relative velocity vector times rho times the relative velocity vector dotted with n hat dA, and that is equal to the sum of the forces. Okay, then this implies that the mass of the cart times the time rate change of velocity of the cart I-hat, and I'm going to substitute in our result above, and I'm just going to copy it. And substitute that in. Okay. And this is equal to the reaction force in the y direction, which is the sum of the forces, minus the mass of the cart, g, j hat. And I should really move this down. Minus the mass of the cart, g, j hat. Okay, well, we know that this here is equal to Vj minus V cart squared. Okay, and that is what we learned from conservation of momentum. And so we have two terms here that involve a Vj minus V cart squared, and this turns into Vj minus V cart squared. I can simplify that and do some algebra. So then this implies that the mass of the cart times the acceleration of the cart dt I-hat plus the density times the jet velocity minus the cart velocity, that quantity squared, times the jet area times cosine theta minus 1 I-hat plus sine theta j-hat, and that's equal to the reaction force in the j direction minus the weight of the cart in the j direction. Okay, so now we now have our full vector equation, and we can start to work with it to find the reaction force and also the velocity of the cart. So first, let's work with the x component. The x component, and that is any term involving an I-hat. Okay, and so what this gives us is that the mass of the cart times dv cart dt plus the density times Vj minus V cart squared times the jet area times cosine theta minus 1 is equal to 0. Now, this is a nice ODE here. We have the mass of the cart, that's constant. This is the density of the water. That's constant. This is the velocity of the jet, that's constant. The jet area is invariant. Cosine theta is invariant, and obviously 1 is also invariant. So in this, this is really a differential equation, and the only thing that is a variant of time is the cart velocity. So we can solve this separable ODE with V cart at 0 is equal to 0 because it starts from rest. Okay? So then this is separable. We can basically move this over to the right-hand side, and then divide both sides by Vj minus Vcart squared. And I'll do it the integral way, but you could do it the standard way that you guys have done in your coursework. So I'll just say that this is the integral from 0 to the cart velocity, because at t equal to 0, the cart velocity is 0, of d v cart over the jet velocity minus the cart velocity squared, and that is equal to the integral from 0 to time of rho over the cart mass times a jet times 1 minus cosine theta dt. Okay, and evaluating the integral, this is a pretty straightforward integral to do, and so I'll just skip to the result. This would be 1 over Vj minus V cart minus 1 over the jet velocity equals rho over the cart mass times a jet times 1 minus cosine theta dt, or not dt, times t. Okay, and we can solve for the relative velocity at any instant of time. So this would be Vj minus V cart equals, and here it's just really straightforward algebra. I just move this term over to the right-hand side, and I take the inverse of it, and I just simplified it. And what this turns into is the mass of the cart times the jet velocity divided by, oops, that was a little too careful with that one, divided by the density of the water, and I'll be careful, now this is the density of the water, not the cart, times the jet velocity times the jet area times 1 minus cosine theta plus the cart mass. Okay, and let's see, there should be a time here somewhere. A jet, yeah, there should be cosine theta times time. Cosine theta times time plus the mass of the cart. Yeah, so I had a little mistake in my notes. I noticed that time was missing, and the reason I noticed that is because I was just doing a quick unit scan in my head, and I just noticed that for the velocity there was a 1 over time, and that was not canceled out by anything. And so, yeah, even if you have a PhD in this field, you still make little errors, and just doing a quick unit conversion in your head to make sure our quick unit cancellation in your head is a very extremely useful way to find errors. Like I just like I saved myself from making. Then we can find the velocity of the cart, and I'll just get and then simplify it a bit, and I'll just skip to the result. It's just algebra at this point. That equals the velocity of the jet times 1 minus the cart mass over the density of the water times the jet velocity times the jet area times 1 minus cosine theta times time plus the cart mass. Okay, so we have now found our cart velocity as a function of time. Then, and so now notice this function, if time is equal to 0, this term here is 0, and we have m cart divided by m cart, which is 1, and 1 minus 1 is 0. So that satisfies our initial condition, and you would expect intuitively that the fluid which is pushing on it will not be capable of pushing the cart faster than it will not be capable of pushing the fluid faster, or it will not be capable of pushing the cart faster than what the water jet is moving. And so what you find is that as time goes to infinity, this term here becomes dominant, and it becomes enormous. And essentially here, as it approaches infinity, this term here approaches infinity, which means this term in the brackets becomes 1. And so as time approaches infinity, the velocity of the cart approaches the velocity of the jet. But as the cart starts moving faster and faster and faster, the net force from the water pushing on it becomes less and less and less and less. Okay, and I'll plot that little function later on. But now I want to find the reaction force, so we'll work with the y direction. Define the reaction force in the y direction. And so I'm just going to skip to the answer, but for that what we had was rho times Vj minus V cart squared, A jet sine theta equals Ry minus M cart times G. And I substitute in our result for Vj minus V cart. That's actually why I separated this out. And I solve for Ry. It's just a bunch of algebra at this point. But what this turns into is Ry equals M cart times gravity plus the density, again, of the water. I should have been more careful with that earlier. Times the cart mass times Vj over rho of the H2O times the jet velocity times A jet times 1 minus cosine theta times time plus the cart mass squared times A jet sine theta. And now notice that the reaction force is 0 if theta is either 0 or 180 degrees. So notice that Ry equals 0 if theta equals 0 or 180 degrees. Okay, and the reason for that being that if theta is 0, our cart looks like this. And the fluid just keeps moving right on by. Okay, and since the fluid did not change direction, there is no transfer of momentum from the jet to the vane, and it doesn't move. There is no force on that. And you can also see that if theta is equal to 0, if theta is equal to 0, cosine theta is 1, which means this term here becomes 0. And we have m cart divided by m cart for all time, which means this term becomes 0, and the cart doesn't accelerate at all. Okay? And so the cart just stays put. And Ry equals 0 if theta is 180 degrees. And what that cart would look like, it'd look kind of goofy, but what that cart would look like would be that the vane would turn the flow completely backwards. Okay, so our water jet would come shooting in over here, get turned around, and then sort of shoot you back in the face. And so essentially then, what you'll find is that in this configuration, the acceleration of the cart is maximized, because you've taken all of this, the momentum of the water jet and completely turned it around. Okay, and that change and the force a force that the cart had to apply to the fluid to stop it in the moving frame of reference, stop it, and then apply a force to basically accelerate it backwards. Okay, and so as you know from Newton's third law, every action has an equal and opposite reaction. That applied a force that accelerated the cart. Okay, and so the acceleration is maximum if theta is equal to 180 degrees. And if you look in this equation here, you can see that that is indeed the case. Cosine theta of 180 is -1, and so minus 1 is 2. And so basically this denominator here grows faster. If it grows faster, then this term here approaches infinity faster, and the cart accelerates to the jet velocity a lot faster. But there is no net reaction force, with the exception of the weight. I guess Ry is not equal to 0. I should say it's equal to the weight of the cart. Okay, and so there is no net extra force produced by the water on the cart if theta is equal to 0 or if theta is equal to 180. Okay, because you could think of, well, to turn the jet up at some angle theta, there is an upward force that the cart is placing on the fluid that basically needs to turn it upwards, right? Well, okay, but then so the cart is pushing the sort of fluid up, and the fluid is pushing the cart down. So there's a net upwards reaction force that is needed to counteract that. But if the angle is 180 degrees, for basically every portion of the flow that we have turned it up, it is being turned. It is for basically every portion on this section here that is pushing the fluid up. There is a portion here that is pushing down to decelerate the fluid so it can stop moving up along this top here. So, and because the forces here that are pushing the fluid up are exactly equal and opposite to the forces here that are pushing the fluid down, to stop it from moving up, those exactly cancel out, and the reaction force is again equal to just the weight of the cart. Okay, so and you can learn a lot from these equations by just looking at them and their characteristics as to what they do with various times. And I was just playing with some numbers here, and if you plot these, if you plot the v cart, what that will look like as a function of time, it will look something like this. I'm sketching it. I have an actual plot, but that didn't turn out very nice. And this is the velocity of the jet. Okay, and then if I plot the reaction force time, and so this is v cart, and if I plot sketch the reaction force, that will look something like this, where this is the weight of the cart here. And so in the very beginning, when the cart is not really moving very fast, the force, even with a fairly weak jet, the downward force on that, the downward force imposed by the water, this was for theta equals 30 degrees, the downward force imposed on the cart by the water can be 4 to 5 times higher than that, 4 to 5 times higher than even that of the weight of the cart. Even if the cart is massive, you can have a lot of force pushing down from the water. Okay, and as a practice problem, you guys, there's a really good one that you can do, that if the cart is moving at constant velocity and not accelerating, you could say that we have the cart, it is on wheels, and it is moving at some v cart I hat, and this is constant. And to keep the cart from accelerating, you're going to need to apply some horizontal force that is needed to basically hold the cart so it stops accelerating. Okay, or it's even pushing against the fluid. And if you reanalyze it for this case, what you'll find, as you can do this as an exercise for yourself, is that the force required to keep the cart moving at a constant velocity Fh, that is equal to rho times Vj minus V cart squared times A jet times 1 minus cosine theta. Okay, and the reaction force, Ry for this case, would be rho, this again of the water, times Vj minus V cart squared times A jet times sine theta. Okay, and so I'll let you guys do that on your own as an exercise. You have to go through almost all the same steps that we did to solve this problem, except for there is an extra force in the free body diagram, and there's no acceleration of the control volume.